A coil is moved from location 1 to location 5 through a magnetic field as shown. The field inside the rectangle is uniform and directed out of the page, and the field outside the rectangle is 0. What would be the direction of induced current in this coil when the coil is at position 5 as it moves to the right? Alright, so even though we have moving charges here, the charges there, they're not moving through a magnetic field. And so for that reason, there shouldn't be any current at that time. Now, what would be the direction of induced current in the coil when the coil is at position 4? That is this position right here. Alright, so at that time, the magnetic flux through the loop is changing. And you just want to do what we did past few problems. Try to analyze which direction the flux is going originally, and then how is that flux changing with time. Alright, so there are actually two ways to analyze this. One would be using the flux, like I mentioned, but there is another way as well, and that would be just using the right-hand cross product rule for moving charges. What I mean is, we've got one portion of the loop moving in a region where there's no magnetic field. And so for that reason, there would be no force for that part of the loop. But over here, on the left side of the loop, we have particles moving through a magnetic field. And so we could analyze that with the right-hand rule for cross product to determine what the force on the particles would be. Now I'll see if I can draw this in 3 dimensions. I'm saying that we have a loop which is partially in the magnetic field region. And in that region, there are field vectors coming out of the page like this. And the wire is made up of metal, which is positive and negative charges. So if you think about the positive charges moving, they're moving to the right here. That's the V for them. But then there's a B field pointed upward. And so the right-hand cross product rule would apply to that section of the wire. So point your pointer finger in the direction of motion of the particles. Your middle finger has to point up like that. And so we've got V for the particles. And I'm just doing the analysis for the positive ones. And then B is the middle finger. That's this. And then the thumb gives the direction of the force on the positive particles. That's from the formula F equals QV cross B. So these positive particles are going to feel a force, which makes them want to go this way around the loop. And so that is one way to figure out what the direction of current must be. It must be counterclockwise from top down. So yeah, I would say counterclockwise from top down. Okay, well, there is another way to analyze it, though. We could also look at it from the perspective of flux. So when it comes to flux, we look at the before and after. So before, we've got field lines coming through that loop. After, though, there's less field lines coming through it. And so initially there's a flux directed upwards. That flux is decreasing. And so we need an induced flux that's going to replace the missing vectors. So this would be B induced. And we got to think about what kind of current would replace those vectors. Just grab the wire with your right hand such that the fingers come through from bottom, like this. And then what happens is the thumb points in a direction that's counterclockwise for the current. And so both of these rules are supposed to be in agreement with each other. Two totally different ways of analyzing it, but we get the same result. What is the direction of the current at position 3? There should actually be no current. The reason why is if we look at the loop now, when it's fully within the magnetic field, I will move it now to the middle. Now, two parts of the loop are moving through the magnetic field. And let's just draw those B vectors again. All right, now, if we do the right-hand rule on this part of the loop, a magnetic force is going to make the positive particles want to go counterclockwise. But if we analyze this part of the loop and do the cross product rule on that, same kind of thing will happen, but the magnetic force opposes the other side of the loop's magnetic force. And so what ends up happening is positive particles, they want to go counterclockwise, but they also at the same time want to go clockwise. And so all this is going to do is just polarize our loop. So we're going to get an accumulation of positive charge on one side of the loop, and we'll get an accumulation of negative charge on the other side. So the loop becomes polarized, but no current flows in a complete loop in this case. Now we can also analyze that according to the flux. So when the loop's in the middle region, before there was flux directed up through the loop, And then when it moves to a new location, there's still the same amount of flux directed upward. So the flux would be called constant here. And for that reason, we will have actually no induced current. Because the current doesn't have to replace any missing flux or stop any increasing flux, because flux is constant. What we would see then, if we analyze all the different positions, is no current here. We would actually have a clockwise induced current when the loop first starts to enter the magnetic field. We'll have no current at this position. Here our current will be counterclockwise. And over here we'll have again no current.